Ken is Edgar Pierce Professor of Psychology at Harvard, and Ken has a history here in California. After he did his bachelor's degree, he did a PhD at UCLA, and then happily came to Berkeley to do a postdoc with Horace Barlow. And most of you know Ken. He was at Smith Kettlewell for many years, and since about 1990 or 91, he's been at Harvard. He comes back to Berkeley, which is to our great fortune, and we are happy to have him here to give a talk on some of Ken's most famous work on surfaces, mid-level vision. Thanks, Ken.
Thank you, David. It's a real pleasure to be here. As Dave said, I have roots in Berkeley. In fact, my mother used to tell me about Berkeley as a magical place. I used to live in New Jersey, and she talked about Wheeler Hall. I never knew what Wheeler Hall was, but she took a chemistry lecture in Wheeler Hall and things like that. And my dad went to Leonia High School, where I grew up, and in New Jersey. And of course, Berkeley was such a good school that my father had to do a year at Berkeley High School, just do penance, and then he got into Cal Berkeley. Most of his stories that he told me of his youth were about being humiliated at Berkeley High, but ever since then he was fine. Okay. So anyway, so I'm here. It's a real pleasure to be here. I'm going to give a talk on things that I've done over the last 25 years, so it's not going to be that new, but I'm trying to synthesize things. You get to a certain age, you want to sort of pull things together. And it's also a talk about phenomenology, which has sort of lost its luster in recent age. I'm trying to bring that back. So the two purposes of my talk is to talk about mid-level vision and subjective contours in particular, because I think subjective contours, rather than being just some curio, they're actually a sort of a litmus test for a kind of processing in the brain that is very important. It's actually a signal of what I call a bounding contour, and it's almost, you can put electrodes in the brain or do all kinds of things, but this is actually a very important signal in the brain. I think it's much, I don't want to say it's more telling, but very telling. The other issue here that I like, the other sort of theme, as I said, phenomenology, another thing that comes back from San Francisco, of course, is the exploratorium. And I was when I first came to Smith Kettlewell, I became friends with Jack Loomis, and we used to spend a lot of time at the exploratorium. Some of you people of older set probably might have known Frank Oppenheimer, who was a very interesting character who believed in the sort of experiential aspect of science. And one of his views was that science has become so ridden with technology and concepts and statistics that one loses sight of the primary data. And it's one of the things that Frank espoused was sort of have a primary experience of some kind of phenomenon that leads to understanding. And so what I'd like to do, and this is something I'm sort of struggling with my colleague Barbara Gillen, we're thinking of writing a monograph for an intelligent audience, introduction to perception, but to a large extent through vision or mid-level vision, and using subjective contours as a kind of as a theme. So let's just proceed a little bit. And if you can't hear me, I'm sitting down. You tell me, and I'll stand up a bit more. So, are subjective contours? Some people call subjective contours illusory contour. Are they illusory? When you say the word illusory, you mean error. And we're all familiar with that. There's many kinds of particular demonstrations that we spend our time creating, which are not veridical in the sense that what you see is not what's, quote, there in the world. But subjective contours are not errors. They really link to some real aspect of the world. And so I think that's a key point that I'd like to make. If that's the only thing you remember, it's an important one. In many ways, they're more real than what are called image contours. Here's a subjective contour here, which represents the boundary of some object, and here's another subjective contour here. Those represent real contours in the real world. Now, David Marr worked on the idea of trying to get contours from the raw image. He had a particular set of algorithms which he tried to doing filtering, getting zero crossings. When you do that, you get stuff that they're not really the contours that we perceive. But subjective contours here, these things which are not present in the image, are more real in a sense. By the way, if you want to shout and contradict me, please do. So and here's a situation where you have a very real what you see in that situation, the image contours, in a sense, are not really very strong. But let me go back to that. And maybe, David, you have to pass out these glasses.
They're on their way.
Oh, they're on their way. Okay. So these are red-green glasses, which I think there's enough for this crowd here. Yeah, there probably is. I'm just guessing. I have about 65 of them, so I'll be fine. I just need one for myself. So another, let me just play this here a little bit more. So if we look at this particular picture here, we see all kinds of contours here, but that's, oops, what happened here? But that's not the real thing that's happening here. It's in a sense, and if you didn't know what those contours were, you might be in trouble if you're swimming around in that area. So it's important to get the real contours. Now, no, that didn't come out. That's okay. Can we pull this down a bit more? I don't know. Yeah, that's fine. So another kind of subjective contour, most of you are familiar with them, and not called subjective contours. I hope this will be a test for your stereopsis. Most of you can see the triangle in front there. There's no real...
But you have the glasses.
Well, yeah, but there's more glasses around. You just have to get them from people.
Left on the
green on the right eye. Yeah, this is what you're green on the right eye. So everybody should have a pair of glasses, unless you're stereo blind, then you'll just have to sort of be bored. Okay, so Bela Ulez essentially introduced into vision the computer, which is a really important step. But these are subjective contours as well, although they're often not labeled as such. Random dot stereographs. So what are subjective contours? Well, I want to just make a few sort of claims here. Subjective contours are a reflection of a critical yet otherwise masked process that identifies the bounding contours of surface objects. They're important because they reveal critical intermediate steps in everyday vision that have been more or less ignored. Maybe you're going to argue with me. Ignored? What do you mean by ignored? Well, the subjective contours are part of a field which I call mid-level vision, which I will make the claim, and you can contradict me, I hope you do it successfully, that this field has been kind of ignored. And I'm going to give you a little short history of mid-level vision, and then just a 3 or 4 minute history, and then we'll launch into things. And it's an updated summary of a chapter that I wrote back in the early 90s, which basically talked about this level of mid-level vision. I did this with these folks here, Jizhang He and Shin Shimojo. And I just want to review some things that have been done over the years. We'll talk about these particular people here. First of all, we have the Hubel and Wiesel receptive fields, which influenced our field tremendously. In fact, they put a number of us to work. They gave us jobs. And then Hubel and Wiesel found higher levels. So these were the simple cells, and they basically were sort of on and off regions. And then we can concatenate those cells here, and then we can even do different kinds of circuitry. Barlow talked about a kind of motion detector. But the basic idea was, in a sense, just a neural incarnation of Frank Rosenblatt's multi-layer perceptron of different stages. There wasn't nothing really special about them. You just have some kind of higher level cell which gets fed by a lower level cell. You have weights, and you can predict the fire rate. So basically an integrate and fire idea. And of course Barlow made this point and said, well, you can just generalize this. And he says that perception corresponds to the activity of small selection from the very numerous high-level neurons, each of which corresponds to a pattern of external events of the order of complexity of the events symbolized by a word. Now, of course, that didn't go unchallenged. That was 72. In the 80s, Marr came along and said that's way too simple. We have to understand vision in a more sophisticated way. We have to think of it in different stages with different characteristics. We can't just think of it this way. And he came up with, I'm just oversimplifying Marr to some extent, several stages. And the 2.5D sketch was, for me, it's a very important one. And for Marr, he says, for all these reasons, the emergence during the autumn of '76 was the idea of the 2.5D sketch, which appeared in Marr Nishihara, which was for me the most exhilarating moment of the whole investigation. So Marr postulated an intermediate stage, and I'm going to sort of pick up on that, and because that's the kind of thing that we did when I worked with my colleagues, my esteemed colleagues, Shinshimojo and others. So, and we made the claim that higher function requires an input, a data format which explicitly represents the scene as a set of surfaces. And I'll explain this to some extent. So, and we actually, to jump ahead, we actually put it somewhere in early vision. It wasn't made in V1, but maybe a little bit in the early parts of the visual pathway in retinotopic cortex. And so, what's been the scientific impact of this idea? Well, for me, I think it got me my job, but I think, other than that, I don't think it's been very much. I think I'm grateful. And sometimes when this was sort of my best work, but I don't think it has influenced the field that much. And I'll give reasons why, and I don't think it may not influence the field, but that's why this talk is a bit of a review. We don't know what's going to happen. But what's happened, in a sense, is people have sort of just skipped it and said, well, you know, let's not bother with that, and we'll just go straight to object recognition. And we have features of things, and then and machine vision, we just brute force, we'll just look at objects, we'll make objects. We just use some kind of a more glorified version of this. And there's some smart people. They have Jim DiCarlo and Cox and his collaborators have talked about recoding the image so that you can find a hyperplane which makes the difference between between your grandmother and somebody else's grandmother. It's not just a grandmother self with one view, but many different views. And that hyperplane, slicing with a hyperplane is basically the same thing as doing something like that. Oh, how come that got so dark? Okay, what happened? It's basically an integrate and fire kind of model. And Shimon Ullman has basically said the same thing, and Shimon Ullman is probably the greatest critic of what I'm going to talk about. So we have haven't had much influence, and why is this? And I think there's very good reasons. I think the problem is that thinking about surfaces, which I'll tell you about, there is no real obvious neural mechanism that one can just pin. The idea of an integrate and fire neuron, sort of the perceptron or the Hubel and Wiesel type of thing, is just so intuitive. We don't have anything else. Plus, you know, people do other things. They have fun doing other things. They don't have to do this. But there are consequences by ignoring the level of service representation. And this NHS stands for not National Health Service, but Nakayama, Heydt, and Shimojo, 1995. And it has consequences for motion, stereops, visual search, texture, object recognition. And we wrote that in our paper. And I'm not saying the paper's been forgotten. It's been cited a lot, but many people cite people and then forget it. But I just like to say, basically, it's incomplete. And I just like to give, not to go through the kind of long arguments we did in the paper, it's too long. I'm just going to give a couple of few little demos that make my point, and we can take it or leave it. As I said, this is an experiential kind of thing. I want to just, the purpose of, I'd like to write a monograph where the reader and the writer are on an equal footing. They will both see the same thing, and you can evaluate this. So this is sort of a dress rehearsal for that kind of effort. Hopefully we'll get it done eventually. So with motion, we can think about motion. How do we regard motion? Well, we've got receptive fields that are sensitive to motion. Barlow and Levick and all, 50 years of, is it 50? Yeah, close to damn 50 years. 48 years. Gerald's got the right number here. I could count on Gerald this. Barlow and Hill, right? Is that what it was? Okay. So anyway, but we need more than this. So why is that? So let me just show you. Let me just do something here. I've got to show you. So this is what's now I got to do a little bit of trickery here. What happened to those guys? Oh, here they are. Okay, you have to sort of bear with me for a minute. So these files disappear, but I can find them. Okay, here they are. Okay, one. No doubt you have seen these things before. So this is a nice work by Maggie Schafar and Jean Laurenceau, is that how I pronounce his name? And these are, the motions are going to be, let me just see if it's, let me just try that. Let's see. I think I looped this morning here. So the motions here, and the motions here are identical. But most of you will see a coherent motion on the right and sort of two sets of motions on the left. So if we think of motion-sensitive neurons in the brain, sensitive to the leftward and upward motion, they give the same signals. Now, we know about intersection of constraints, atalus and motion. That really doesn't handle this because you have to decide whether those sticks are the same object or a different object. And on the right, they complete behind those, quote, occluders there, and you see them as one object. And there are many other examples of this that have been nicely documented, and this is just one of them. Stuart Ansys has something called the chopsticks illusion, and many different other people have very nice demonstrations. So I don't think we need to dwell on that. Okay, so now I can get rid of these guys here. I'll just jump ahead here. I think they'll just sit in the background here. Okay, so now let's just jump a little bit ahead to object recognition. So we've got some very nice work by Keiji Tanaka and many successors where you find very complex receptive fields in the brain. But you need more than that. You really can't do object. I mean, it'll go quite a bit of the way. And machine vision is done very well, particularly recently. But it's not. It doesn't really match human performance for object recognition. So why is that? And here's something that I generated with Shin Shimojo years ago. This is a test of your object recognition. You see an upside down U and a right side up U, but then you see an O here, and then here you see a C. So, in a sense, your visual system, even though that black area is the same, you parse or deal with the image in various ways, and your visual system makes it continue behind, and it becomes essentially a different object. And the same thing happens in face recognition. I generated this picture here long ago, and if we look a little bit at one of those bars there, we can see that if we have a face recognition algorithm here, and we try to recognize that face there, the algorithm is just doing kind of template matching, and basically, what do you do with that line there? Well, you got to get rid of that line there. When you're doing face recognition, that's not part of your face, okay? So we got to get rid of it. So what we did was generated a picture here and put the face in back. Over here, the face is in front. Sorry, the fragments are, oh, sorry. You can see the face there, but when the face is in front here, you got your pictures here. Basically, you notice that when the faces are in back, you somehow discount that border and you see the face very nicely. But when the face is in front, basically it's very hard to see. So when I'm claiming, among other things, that the bounding contour defines object, shape, and identity, there's something called the one-sided nature of the bounding contour. Nearly the contour belongs to something, it doesn't belong to something else. In this particular case here, the contour belongs to the blue stuff, and so essentially this black area is unbounded, and this is unbounded, it can connect up. So that's something that I made a big deal about 15 years ago. And as I said, the unbounded regions can link up together to form objects. And the same thing happens here. We just reiterating this, and you can see this here. You can see that we'll get to this, we'll come back to this again, but you'll see a C here, and you'll see this pattern here, because this stuff, it turns out then, when stuff is in front, the object completes in back. Most of you should see on the right a C, and on the left you should see sort of two separate objects. So, in a sense, in all these different situations, the borders of these image regions are important. You have to decide, the visual system has to make a decision whether the border belongs to one region or another region. So, low-level vision just can't compute object motion without surfaces, ditto for high-level vision. You have to have some kind of level of what I call a surface representation. And I just want to say that these are toy situations here, but we can also just make it a little bit more realistic and look at just some natural scenes here. Here are objects which are defined mainly by their bounding contours, and most of you can recognize them. So the bounding contours of many objects render them render them recognizable. We have so what I'm trying to say is that we have let's say of a scene like this, and what I'm going to do is make a sort of a somewhat outlandish claim that the visual system actually computes the bounding contours of objects, and that's an input to object recognition. So it does something like this, and then we have the bounding contour here, and so they basically, I claim there exists a hidden process that identifies the bounding contours of visible surface for the purpose of recognition. You don't see the process.
Isn't this a bit of a chicken and egg problem? Because you have to find the object to do object recognition. So how is that happening?
That's what Shimon says. So I understand. We can get back. We can get back to that. And I think that's an important debate. But then I don't disagree with him entirely. So, but I think there are mechanisms that give you the bounding contours in addition to not getting the object. But I think this is a key thorny point. So what's the evidence that there are, well, aside from how you do it, Hani's question is, how do you get those bounding contours? And that's, I'm not discussing that right now. I'm saying that they exist. Now, so I have to get to that point first. And I got to give you the evidence for it, or at least take a stab at giving you evidence. So what's the evidence that these bounding contours are? Well, I think some of it comes from a little place in France, anonymous 30,000 years ago. Somebody scratched stuff around, and all of a sudden, wow, they could somehow depict objects with a tremendous amount of veracity. And as most of you know, that these cave paintings were discovered about 16 years ago in France, and there are many others in the world. But you can see just by skillful scratching or making marks on a wall of a cave, many hundreds of feet into this cave, you can really depict, and you can have things like these are also bounding contours of an animal's leg and things like that. So these are really extremely depictive, and it's almost as if the bounding contours of object, if you just draw lines, you have a visual code. Later on, if you go to a How to Do It book and stuff like that, you find that the line drawing is actually just as good or better than the photo. And so many, if you try to repair your car and stuff like that, they show the picture of the engine. The line drawing is often better than showing the photo, because a lot of the contrast is lost in pictures and things like that. Okay, so my colleague Patrick Kavanaugh says there are no lines in the real world correspond to these lines used in drawings. So he suggests, I'm paraphrasing, it must be some kind of elemental visual code easily discovered by our hominid ancestors. So that's my evidence. I have a little bit more evidence. Rudy von der Heydt has found some cells in V2, which he called border ownership cells, which could be candidates for such a representation. And what's interesting about von der Heydt cells, in contrast to the work of Hubel and Wiesel, you notice in this particular cell fires for the light and dark border here, and then a dark light border. Why is that? Well, the reason is because on the let's say you were an ant rolling along here, on your right would be the surface that owns that border. This is a small object. Rudiger found that small objects, in a sense, become any contour surrounding a small object, in a sense, owns that border. And so bounding contours are not features in the sense that image features. There's something more abstract. They're surface properties, and they're critical for object recognition, and they're one-sided. So how does the visual system determine boundary contours? Let's say, this is the question that Hani brought up, independent of recognition. Well, I'm going to cheat a little bit, but I'm just going to give you an example. This is a stereogram some of you will have trouble with, and if you have too much trouble and get headaches, I apologize. This is a really weird stereogram, but I couldn't resist showing it here. Left, and when you first put it on there, it just all becomes diplopic and it's kind of horrible. But try to fixate on this faucet on the right here. Just try to fixate in different planes. Anybody, I don't know. I know Suzanne has very good stereocuity, but I don't know if she has high tolerance for large disparities. Anybody getting the scene here? Yeah. Okay. So in this scene here, what you see is there's all kinds of stuff. It's a very complex, interesting scene, but let's talk about border ownership. Well, borders are usually owned by the stuff in front. That faucet sitting here in front here, well, there's something in front usually owns the border. So that, and small things own the border. And the only other point I want to make, it's something I call entropy. If you take any object, those coffee urns there, just trace your eye around the perimeter of one of those coffee urns or any other object in front, and just think of the stuff on the other side of the coffee urn. It's very heterogeneous, and I call that entropy. So I'll just proceed here. So these are some of the properties. This isn't the whole list. There's some things that help how the visual system makes that decision of whether something owns the border or not. One of them is depth. One of them is bound by the smallness. I call it convexity, and I'll talk about that a little bit. And disorder, entropy. So the entropy thing, I'll give it. Forget the thing on top. I should have skipped that. There's a nice experiment done by my colleague Barbara Gillum on entropy. So you ask people. They give them 3 types of objects here, and these are more disordered here. The range of orientation here is much more than here and much more than here. And you just ask people, is that an object or a whole? And probably most of you can see that this is more like an object, and this can look like a window with something passing through. So already, just the idea of disorder as background is a possible cue, in a sense, a local possibly bottom-up cue for establishing border ownership. Another one that Rubin, Gerald, when did Rubin publish his paper? 1911? Something like that. Edgar Rubin, who is really one of the grandfathers of these ideas, indicate that the smallness is important. And Kanitsa has a very interesting demonstration as well, because people think, well, symmetry might be important. It turns out that symmetry is not as important as the convexity or smallness, as the next demo will show you. You're going to see another demo, and it's going to be one of these ambiguous things, but what do you see here? You see the black things here and the white things here, or vice versa. It's not perfect, but most people tend to see the black things initially, and then it's bistable. But the black things here are, if you notice here, they're really convex here. And even though the white stuff here is symmetrical, it's not the thing that immediately appears. People have done experiments on this, and it's not perfect, but you tend to see the convex region. Okay, so finally, the talk was advertised as subjective contours, that sort of background. So one of the things that I got into perception, I got very interested in perception, was to come with a physiological understanding of perception, essentially. That's when I was a grad student. And as I've become more into my career, that sort of goal seems to be further and further receding. I thought I did it when I did my thesis, but somehow it seems to elude us. But maybe some of you are more see it as a more closer. The shore is closer. So let me just talk about a couple things here. One of the things I did with Shimojo was something called Da Vinci stereopsis, which basically is a sort of recognizes the fact that Leonardo, in his essay on painting, his view about binocular vision was different than Wheatstone's, and he basically said the reason why you see enhanced depth was that when your one eye can see around an object, your right eye will see this region behind an occluder, and your left eye will see that, and hence that's the reason why we have depth. He was right, but he didn't do an experiment or something like that, like Wheatstone did. And so what one can do here is I could just set up an experiment here where I could just, every day of your life you have occluders here, and it just happens all the time, and there are unpaired points here. And here I'll just have a demo here. We have a bunch of unpaired points. This is not stereo yet, but the next slide. What should we see in a sense if these spots here are only seen by the right eye? Well, the answer is we should see if I'm right, we should see a ghostly surface, a subjective occluding contour, and I think something like that. And you'll see that here. If you look there, I don't know if I can see it from here, but your green has to be in your right eye. Top or bottom, where do you see the subjective surface? Should see a very sharp little surface along here. You don't see anything like little subjective contour there? Okay, doesn't work.
Can you turn off the lights?
No, that won't help. I'll do another demo. These sometimes don't work. This one's better. Here's another example where I'll have left eye only and right eye only. and you'll see on the right or left, you should see a subjective surface here. I really can't look here. So you see it's kind of a square in the middle. How many people see a square on the right or on the left?
On the right.
And what's happening on the right is these dots here are seen only by the right eye, and these dots are left eye. You can close your eyes, and we'll alternate them to check and see if I'm correct. It's not perfect because there's a little bit of bleed through there, but that really works. Well, it makes sense because you've got, you know, this, as I said here, you've got this is the geometry of the situation, are we conscious of which eye is stimulated? I mean, you can try things like this, and you know, most of us, unless we have unequal vision in both eyes, something like that, we really find that kind of hard to do. So we made the case, and I don't know if we're right or not, but that because eye of origin information is lost in early vision, in a sense, by the time you reach V2 or V3 or something like that, you don't have right eye or left eye cells and things like that. At least the signals leading to these subjective contours are pretty early, and so we put them around V2. Now, of course, that was, in a sense, nicely confirmed, in a sense, by the work of Rüdiger von der Heydt, who, in about the same time in Switzerland, found cells that this is a tuning curve for a real contour here and a tuning curve for a subjective contour. Basically, the contours like this. These are, for those in the back of the room, if you can see that, there's a kind of subjective contour here where these little lines are not interdigitating, they're abutting, and Rüdiger von der Heydt found that these cells responded similarly, maybe not as strongly, to these contours, even though these were not, there was no image energy at that location. And I happened to have the pleasure of working in Charlie Gilbert's lab quite a bit later, and we set up some different kinds of stereograms here, and you can notice here that the stereograms here, you notice that on this stereogram here, on the far left, you see a kind of a vertical stick in front, and you see a subjective contour, a vertical subjective contour, and on the right you see likewise. So just by manipulating the sign of disparity in these very sparse stereograms, you can make very strong subjective contours. And in Charles Gilbert's lab, we did things like that in the monkey, and we fiddled with the disparity, and we made a subjective contour here, and we found cells that were more strongly activated for the subjective contour. So, but could we write, just as like Hubel and Wiesel or the perceptron, can we write a circuit diagram or a kind of a, what shall I call it, at least a plausible diagram of how this is done? And this is the part that I'm not sure of. This is the kind of point of this talk here. Now, there's many different models. I was going to the simplest model that was proposed by Rüdiger von der Heydt a while back, where he had essentially end-stop cells, which these are end-stop cells right here and end-stop cells here, and their receptive fields are organized in such a way such that, and they are linked together into, into some kind of master cell here that would be a detector of subjective contours. And one of the nice predictions of such a model is that if you interdigitate things like this, like here, these cells, there'd be no cells doing that. The cells are sensitive to abutting, and there's no abutting there, and so therefore you shouldn't get any subjective contours. But so what I will do is show you in situations like this that if you think of the scene as a three-dimensional scene, that you will not have a subjective contour here, and you will have a subjective contour here, because that's the way your scene interpretation works. And so I'll show you in the next stereogram here. So basically, when they're interdigitated, you shouldn't see a subjective contour, and where they're abutting, you should see it. But I'm going to show you some stereograms where you would predict that you should see subjective contour here, but you don't, and you do, and you don't over here. So why don't we just look at these things with our stereo glasses again? So here, there's all these sticks are all different depths here, and there's no occlusion in a sense, no bounding contour in a sense, and there's no subjective contour. Whereas over here, not for everybody, but many of you will see a nice subjective contour with actually sticks poking through on the right. How many see that on the right there? So it indicates that we can't really we can't look at the scene just as a two-dimensional scene. We have to really see that our visual system is always interpreting the scene in 3 dimensions. So some of the factors, and I told depth, opacity, and things like that. So one of the things I want to I think I'm going to talk about this. Oh yeah, Barbara Gillum did a very nice chapter in a book, and she just did a sort of one-off thing. She just generated this about entropy. So this is a really nice demonstration of entropy here coming up. So she just drew this on a piece of paper, and it's very striking. Subjective contour on the right is very strong, it's not on the left, because in a sense that disorder in the background is some kind of clue, and those models don't predict this at all. This is a kind of a process. So basically I'm just trying to say that somehow in evaluation of the environment, in terms of sort of ecological approach of what background is relative to foreground. Another thing about it is I mentioned the cave paintings. Here we've got the next slide here. So we see nice subjective contours here, but we don't see them here, because in a sense these are the visual system has its code. The line is a bounding contour, and there's no subjective contour here for the same reason that we depict the outlines of objects, and there's no reason why there should be anything occluding this here, because these are full objects in themselves. Okay, so this is I'm sure this is the last demo, I'm not sure. This is the one that Barbara and I cooked up, was very satisfying. So what is an occluding surface, in a sense? What constitutes an occluding surface? And we call this, maybe we need a better name, but I call it the forest versus the plane. Did I skip something here? No, I don't think so. So what configuration is more likely to be an occluder? Here we have a bunch of sticks here, and they're all sort of random depths, and we have a bunch of sticks here sort of that are actually coplanar. So if something's coplanar, it's more likely to be a surface, and it's more likely to occlude. Reasonable? So what we did was we called this the plane, and we called it with a putative plane, let's call it, and we'll call this the forest. And does the visual system know this? So, and now this is the sort of the idea of using subjective contours again as a litmus test for deducing, for the visual system to know whether something is an occluding contour. Normally we don't have that litmus test because we have an image contour here, but when there's no contour here, the visual system must create it, because that's the most probable cause of the images that you see. So here's the idea. You're going to see stereograms coming up with a bunch of sticks on top and a bunch of sticks on the bottom. These will be closer. These will be far and close, far and close. And in one case, the sticks will be all coplanar. Here they'll be all in one plane, and here they'll be kind of varied. And so the prediction is that you should see a subjective contour when the plane is in front, not when the forest is in front. So here's the plane in front, here's the forest in front here. So you will, on the top you'll see a nice subjective contour dividing those two areas, and the bottom you won't. Okay, well, I can't. There's always somebody who's going to. But if you did experiment with this different. Now, what I would argue what you should do is scrutinize this border here. Put your eye, just run your eye along here, and run your eye along there, and maybe the difference will become more apparent. Maybe even Suzanne will be convinced. I'm not sure. I can't. What is it? You can't please everybody. What's the word? Not Abraham Lincoln. Anyway, so here we go. So that's sort of, I'm not saying that this is a bad model, but it's just incomplete. I think that when we think about subjective contour, we can't think of it as a 2D image. We have to think of what Whitman Richards used to call image understanding. We have to say, and then a nice situation here is that the interdigitation doesn't cause any problem here. You see a nice subjective contour, even though those lines are poking through there. So how intelligence is intelligence in a sense? How intelligent is the system? I did something wrong here. There's got to be a mistake there, right? Okay. So anyway, I'm going to say not very. And I'm not going to make a long thing about this. This is something, a paper that Shin Shimojo and I did in Science a while back in the early 90s. It was sort of prompted by a kind of, we showed stereograms that should sort of look like this, but ended up, the person should be looking at sort of folded cards, but actually what the person saw were transparent surfaces. And I don't want to go into details here, but it's too long. But basically, we instead of trying to build a circuit diagram for mid-level vision and subjective contour in particular, we argue that we really can't think of that's sort of too hard. We really can't do that. The brain is sort of a neural network, and we have to think of it, the visual cortex, as a learning machine. And our idea was that if we had a set of candidate surfaces here, like many different surfaces that were possible in the world, when you locomote through the world from all different vantage points around a particular surface, you're sort of going around this viewing sphere. There's a surface here, and you go around this viewing sphere. This omega over 4 pi, in a sense, is essentially your exposure to that particular image. And when those things are very large, you get a strong strength. And so the idea was that when you're faced with an image, some image which is really basically given a particular surface, you get a particular image, how big that solid angle is a sort of a predictor of your learning strength. You'll see that. And I won't go into details here, but we could make this case for many of the things that we saw here. I'm just not going to do that here. So I'm going to conclude here and say, our visual system identifies the bounding contours of surfaces via experience. We literally see these inferences when we see subjective contours. So subjective contours are not a curio. They're actually a litmus test for a very important process in our visual system to identify the bounding contours of objects that really help in perception. And as I said, we make the claim, and not really spoken about a lot here, these inferences could arise from associated learning. And I'd just like to make the plea for a continued expanded role for phenomenology, which sometimes is forgotten in all of our great scientific endeavors. So I'd like to acknowledge my collaborators, Barbara Gillum, who I did most of the work when I was at Harvard. She visited me a number of occasions. Of course, Xi Zhang and Shin. I just want to say one more thing because people will always come up with the thing, well, maybe there's very high-level things here, and this is where I acknowledge my colleague Peter C., who, I got off the World Wildlife Foundation, but Peter's come up with all kinds of particularly very cute little subjective contours that he's very good at creating these little funny things. And you see subjective contours here, and even here, this is kind of an interesting thing where you see subjective contours, but, and this is the part that's kind of fun, and you could do this right now, you see this as kind of rings in front around a pole, but what I want you to do is just exercise your mind a little bit and imagine these are as little bracelets with openings, and they're just like that and facing you, the open end facing you. And if you just put your mind to it, and all of a sudden the subjective contour just vanishes. So with that with that final demo, I thank you very much.
What kind of role do you say top-down influences have in the perception of these?
I think that's a big issue. I think that's the thing that Hani raised, and I think it's extremely important in cognitive science. I don't think we know the answer. I'm proposing a particular line, and I don't think I'm wrong, but I don't think it's exhaustive. I just think that the visual system is probably a very complex system, that high-level things interact with low-level things, and this is something that is, there are models that people have discussed this, and this is a very important process. Shimon Ullman, I don't see, where's Jatindra? He's not here, because Jatindra Malik has been trying to say that these things can be generated from the image, in a sense, and Shimon Ullman has some very strong demonstration showing that doesn't work. And so I think this is, I believe that even something like this indicates the importance of top-down information. But at the same time, I don't think it negates the idea that the visual system can use low-level information to do this. Stan.
What about doing it with timing, brief exposures or mass, to see whether top-down would take more time, maybe?
Right. I think there's a work, Nicola Bruno and different kinds of people have worked. I think Alison Sekuler's worked on this. She called it microgenesis. Her idea is that in the beginning there's Now, that Allison Sekulev found that in the beginning you have the image and then later on you see the surface. Nicola Bruno said, no, that's not the case. You see the surface right away. My work tend to see that you see the surface right away. I've done a lot of work with visual search and texture segregation, and when we do texture segmentation and we do visual search, I have a paper with Zhejiang, Nature paper, early 90s. Basically, the elements for visual search are not the image itself, but the actual completed objects going behind occluders. So to the extent that those experiments speak to that, that's the point. Regina?
Does anybody know at what age children recognize these apparent contours?
Yeah, I think this is a very interesting issue. I was just visiting Tony Norch recently, and he's one of the few people who is really seriously studying this level of mid-level vision, working with infants. And his view, and if evidence is really kind of indirect, and he hasn't really published most of it, is that infants' visual acuity and contrast sensitivity very, very good at an early age, much better than, let's say, forced choice preferential looking would show, but that these mid-level vision processes in kids are actually quite retarded. But it's not really clear. He really needs to flesh out that research. I think it's a very promising research program that he's doing, but it hasn't really he hasn't really made the strongest statements that he can. But I think that one could argue from his data that it takes a while. But there are many other studies that indicate that there is a lot of mid-level vision processing going on. Very important work by Phil Kelman and Elizabeth Spelke. I'm sure you were at Penn, you must have known that. A very brilliant work in babies about the importance of relative motion and the baby deciding whether two parts of an image belong together or don't belong together. So I think that it's a process.
There's always a conjunction of tactile perception.
Oh, so you're a Bishop Berkeley person, huh? that was his. That was his. You're a Gibsonian, yeah, but Gibson would be very much against Bishop Berkeley. I mean, Berkeley in this new theory of vision basically had this tactile kind of thing, and Gibson would say no. It's all basically you just get it from the image, yes. That you get all the information. Right.
Implicit in the in all of this is that somewhere this is observed, right? And so maybe you have a 3D sketch or a 2D sketch, but the observer, just like in the audience, we're separate from the slides. You're implying there's an observer in the head who's observing, and the question is, at what level does that start? And what I'm wondering is the perception of these things really so separable from the representation? And is there, if it's not separable, what is the implication of that?
Yeah. Okay. So I think that's a little bit like Hani Farid's question. I think it's a deeper question about cognitive science in general, which I'm not going to punt on. But I think we have the similar kind of thing in speech. You listen to a foreign language, and it seems like water just running, okay? And you listen to English, you can't feel that run of water. You just get discrete words. So in the appreciation of speech, obviously your understanding of those words, your encoding of the high-level representation of each of those words helps you parse those images. Now in vision, I think it's a little bit like that, but at the same time, I think there are also lower-level mechanisms at play as well. So I think that it happens at many levels, and just the speech thing is kind of interesting. Just to give you a funny example, Hani will appreciate this. I went to a computer vision conference, and all the people at the conference were either from China or from India, and the ones from India talk very fast. And so I was listening to them I was following them, and then all of a sudden, they were talking so fast, and I was getting tired, and their speech just went into just a long series of sort of music. All I could just hear was, I couldn't hear any words anymore. Some of you can try this out sometimes.
Ken, that was great. Two things. One was an answer for us. Farson has shown that 6-month-olds can recognize moony faces.
Sorry?
6-month-olds can recognize moony faces and objects like the panda here, so they do have surface representation. But my real question was, if there is, to answer the Ullman objection, if there is surface representation or a surface boundary assignment that precedes or object, then you might expect a case where surface assignment boundaries are assigned that violate object interpretations. And that's exactly what the cardboard cutout phenomenon, I think, might be.
Right.
And this is where the visual system is overzealous in its surface assignment, even when it totally violates object interpretation or the object intended representation.
That's a very good point. In fact, most of you have seen Penrose's impossible triangle.
Right.
The impossible triangle is not really an impossible object. It's actually a 3D object that is looked at from a particular vantage point, and that's exactly what David is talking about. The surface representation is so powerful and so overzealous in some situations that you will see an object that is impossible.
We're talking about high level and low level, but doesn't the strength of perception of the surface indicate that that's at the highest level of perception in itself because it's something that you perceive directly? It's not some functional thing like the sounds of the language that we know that you ignore. In that case, what you're really describing is very high level vision.
Well, I think what you're saying is that what we see all the time is high level vision. And I think that's true. I mean, we don't see with our visual cortex, we don't see with our lateral geniculate body. What we see is at the highest level, and so I don't doubt that. But I think that the beauty of psychophysics, at least in my career in the past, has been that there have been these choke points in vision where certain kinds of limitations are apparent, and you can study, that's what we thought. I'm not sure it's true. We thought that by studying the properties, very careful, doing careful psychophysical measurements, even though our vision, our perception is very high level, it's our conscious experience, that there are these choke points or bottlenecks in the processing itself that would, just for example, like the V lambda curve for the cones, we could actually find, even though we're using conscious vision, it is very surprising, we use our conscious vision to actually find the actual biochemical properties of the cone pigments. And so that worked. Now, when you get to higher level vision, I don't know if that's going to work, but it has been extremely successful.
And how important is motion for mid-level vision and for surfaces?
I think it's going to be, I think what motion is going to be, this is just prophecy. Motion is going to be the teacher of the visual system. It's one of these things that objects, it's a very telling. When something's one object versus another object, and you saw that shark moving there, there's no way that motion is just so revealing, even if you don't have stereopsis. And so this is something totally unexplored. It's something that I think some people who are starting out, if they want to make a dent in this area, if that's possible, I think motion is going to be the correlation between motion and a surface or an object or a bounding contour has got to be so important. And so the motion system, in a sense, could train all those other things that I talked about, the small, all those things there could be trained by a motion system. How that's to be done, that's why I put that learning matrix up there. I have no idea. That's for you younger people to figure out.
All right, let's thank Ken. If you can drop off your